Bismillahirrahmanirrahim. Previously we had talked about the perpendicular bisectors and that they were concurrent, and the point of concurrency was the circumcenter, which was the center of the circle that circumscribes this triangle. And the triangle, as you recall, is said to be inscribed in this circle. And then we talked about the angle bisectors. And the angle bisectors were also concurrent, and the point of their concurrency was the incenter, and that too was very special, in that that was the center of the circle that is inscribed in this triangle. So we talked about the perpendicular bisectors and the angle bisectors and the circumcenter and the incenter respectively. Now today, inshallah, we shall talk about the medians and their point of concurrency, and the point of concurrency of the medians is called the centroid. This too is very special. Now you must wonder how this is special, because the circumcenter is taken and the incenter is taken, and you can really only circumscribe or inscribe a circle, right? So how is this going to be special, you would say, right? Well, let's find out. So I have this triangle here pre-drawn, triangle P, Q, and R, and then we're going to draw the three medians. So I'm going to take this point P here, the vertex P, and I'm going to connect it to the midpoint on this other side, and we can call this one, let's call these midpoint. Let's call this one midpoint 1, M1, midpoint 2, M2, and this third midpoint here, M3. And let's draw out all the medians. So that's the median number 1, and from vertex Q to the midpoint of the other side, that would be our median number 2, like this. And let's draw out the third median, and as you recall, these were also concurrent like thus. Ta-da! Now this point is also special, right? So the point of concurrency of the medians, the point of concurrency here, this point right there, okay, that's called the centroid. Okay, so this point right here, this point would be the centroid, like this. Okay, there. So this point is called the centroid. Now what's special about the centroid, you say? Well, there's two things that are very, very special about the centroid. There's no circle that, it circumscribes or inscribes, etc. But there's something very special. One thing that's very special is that this centroid is 2/3 the distance from this vertex to the midpoint. That is, from here to here. In other words, okay, from here to here is 2/3 of the distance from P to M. Okay, another way of saying the same thing, is if this is X, this is going to be 2X. Okay, that's how this is always divided. For example, if this was 5, this segment right here. Now let's call this our centroid point C. Okay, so if C to M3, if this was 5, then this segment from P to C, that would be 10. Okay, now this segment to this segment is always in a 1:2 ratio. Okay, so always in a 1:2 ratio. Okay, so the centroid is 2/3 the distance from the vertex to the midpoint. So if this again was X, so this would be 2X. So this segment right here from Q to C will be 2 times as big as from C to M2. Another way of saying the same thing is that the centroid is 2/3 the distance from the vertex to the midpoint, and this is 1/3, because altogether they make one whole, right? So you say, well, that's okay, I get that, that's kind of cool. Maybe the centroid, concurrent, and so you might be saying, okay, I get it, the centroid is 2/3 the distance from the vertex, so it is going to be 2/3 the distance from here to here, like this, and compared to the whole distance over here. I get that, and you say, okay, I get it. If you tell me if this is X, this segment is going to be 2X, and I get that, and that's true for all 3 midpoints. I get it. And, I'm not sure that's that special. It's not nearly as cool as the incenter or the circumcenter, right? Well, I'm not sure, but look at this though. Centroid is so special. It's got a property so special that even the in-center and the circumcenter, they would be envious, I think. Because the centroid is the center of mass. Centroid is the center of mass of the triangle, so to speak. Centroid. Now, a triangle does not have a mass per se, okay? But in real life, if you were to construct a triangle like this, and you could put your finger under the triangle like this, and you could balance the triangle on the one finger. It's kind of like the center point of the triangle in a way. Now you say, well, which one is the real center point of the triangle? Is the in-center, the circumcenter, or centroid? Which one, like, well, triangles don't have like centers per se, right? The centers are a thing that you describe for like circles. And none of these points are really more important than the other in a sense. But the centroid has extreme practical value in real life because many times we want to balance things. Like if you're walking on in a canoe, right? You have to balance yourself, right? If you're first getting on a canoe, you have to balance yourself. And you do quite a balancing act, don't you? What you're doing is you're trying to keep the center of mass, your center of gravity, in one place so you don't tip over. So you intuitively know your own center of mass or center of gravity. And every object has a center of mass. And the center of mass or center of gravity of a triangle is the centroid. Thus, now if you wanted to balance your triangle on the tip of your pencil like this, the first thing you would have to do is find the centroid. And the centroid is the intersection of the medians, which are concurrent. And the centroid, I think, is cool. Until next time, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.